Welcome back to Decouple. Today I'm joined by Cal Abel. Cal has a 20-year history in energy and energy policy. He holds a PhD in nuclear engineering from Georgia Institute of Technology and served 10 years in the United States Navy working on submarines. Amongst his other accomplishments, Cal was instrumental in the development of the Natrium reactor, and in our pre-episode chat here, I've just learned that he competes in strongman. Cal, as you know, guests here on Decouple introduce themselves. So I'm going to give you a couple minutes to pretend you're in an elevator with one of our listeners and give us the Coles notes. And I'm sure we're going to dive in deep because, as I can see, you're a pretty multifaceted individual.
Oh, so what do I say about myself other than what you already said? I don't know. I kind of wound up in nuclear power. I picked the major because it was hard. I don't know if that's a normal thing to do, but that's what I did. It seemed cool, and I wanted to go into submarines, so I thought, yeah, they're nuclear powered, so why not study nuclear engineering? So that's what I did. It turned out that I absolutely love running nuclear reactors. I'm actually pretty good at it. And I love figuring out how to build them and how to, like, kind of how it all fits together. It's like this giant puzzle, and it's kind of like catnip, and I get to play with it. And so when I got out of the Navy, I was trying to figure out what to do. I had no idea. I mean, you have Navy life and then you have civilian life, very different. So I had no idea what I was going to do or even how to really interact with people. So I used the time to get my PhD in order to kind of reacclimate. It's kind of like a glide path into normal life. Turns out that was needed. Although I did try going directly into commercial nuclear power right after the Navy at Sequoia. The scale of those reactors is unreal. When you have a steam pipe that's the high pressure steam pipe going to the high pressure turbine, as I recall, is around 4 feet in diameter. So a little over 1 meter in diameter. And you'd be sitting there watching the steam flow through it and watching it move back and forth, literally like this, as it's just, and it was designed to do that. I mean, you can just feel literally the flow of the steam flowing through that you could feel. So I guess because my experience with nuclear power has been operational, my sense of it is one of feeling. We would do these head flank cavitate maneuvers on submarines where you'd go from 10% power to 100% power in about 45 seconds. If your throttleman was good, you could get up there. You'd get up to 80% within probably 10 seconds. And then you'd work your way up to 100 from there without trying to overshoot, because then you get a protective action, and then that's kind of not good. But so it really is kind of like the bulk. You'd get to 80% quickly, and then you get up there. But feeling the ship shudder, you could watch the shaft, and I've watched the shaft actually twist, and the shaft is probably about 3 feet in diameter. I've watched it coil like a spring from the force of the steam coming into it and just snap the ship. And then the ship just whips through the water. And so my experience with nuclear energy is one of feeling the power. So that's where my passion for it comes from, is because I know what it can do. I feel it. It's a tangible thing. So after the Navy, I had a love of fast reactors that was instilled in me at Wisconsin in my undergrad and master's. And I have been a fast reactor fanboy for north of 25 years now. I just love them. My work for my PhD was specifically centered on them. So Natrium uses the prism reactor, which is what I took. And so I was like, back it up a little bit. So while I was at TVA, I get bored easily. ADD is a bit of a problem. It's part of the reason why I lift weights, is to help with ADD.
Yeah. Let's unpack some more.
Yeah, sorry. So where do you want to go? Where do you want to go with that? So I did all that stuff. Oh, by the way, I also own about half of a coal mine. So I'm also a coal miner. So
okay.
how did a nuclear engineer become a coal miner Navy guy?
Yeah, we've got a lot to unpack. And listen, I feel like I could talk to you all day about nuclear subs. It's my favorite kind of movie, more kind of World War II sub stuff I find fascinating. Das Boot, obviously, the classic.
Yep.
But also watching, it's this great guy on YouTube with an engineering channel. I'm blanking on it right now. But, his, bringing a crew down on a nuclear sub and just trying to understand the culture of, I guess, these kind of mad men and mad women that will do that to themselves, live
Down
underwater with
Periscope.
yeah, live
Down
underwater
Periscope.
with, such little contact with the outside world, but I mean, really, it's I think the closest you come to kind of manned space travel. I mean, underwater is kind of extraterrestrial, at least off land, and you're in this fucking spaceship, and, I mean, the culture of excellence, I think, is what impressed me in terms of the brief conversations I've seen on YouTube with, submariners is just like, why do you do this? I think it's because you have to operate at such an extraordinarily high level of capacity, understand the whole ship, be able to patch and mend just about anything. I mean, it really to me feels like Deep Space Nine, as an outsider, as an observer. So I've got this little window into it. I could talk to you all day about it. I wouldn't mind, expanding a bit on it, but there is a lot I want to touch on. So here's my laundry list.
Okay,
And
let's
this is
go.
kind of building off of following you on Twitter, reading a guest post of yours on Grid Brief, which everyone who's listening right now should hit pause and go and subscribe on Twitter, and for the email for Grid Brief. But anyway, some of the topics, and we can sort of which ones we want to dwell on more than others. But your thoughts on why variable renewable energy doesn't work. We can touch a bit on energy return, energy invested, and a more sort of meta view of energy. I definitely do want to make sure we don't miss out talking about natrium and particularly thermal storage, why that's better than battery storage. And something that came out of our pre-talk was, I guess, kind of pragmatic versus puritanical responses to decarbonization. And again, you do talk about this idea of swapping in nuclear for coal. We have over $1 trillion of infrastructure that exists that's fossil. But you say that we need to keep shipping the coal to this new nuclear power plant that's swapped in. And we just chatted a little bit about that. And, in terms of who turned me on to your work, that was largely BF Randall, who sort of blew up the whole podcast with our diesel powered decoupling episode. I think another example of of pragmatic versus puritanical decarbonization. So those are kind of my priorities. I've been listening a lot to a guy named Nate Hagans, who paints a fairly dark picture of the world as we sort of use up this carbon pulse, which is kind of what underlies, the last 200-300 years of the incredible blow up of population, of innovation, of technology, of everything that's around us. And he really posits that fossil fuels are just too good; they're impossible to replace. And I have to say, I sort of agree to a large extent. They're just so such concentrated forms of usable energy, and the challenge of decarbonization for me isn't just making clean energy; it's replacing fossil fuel services. So I think, in terms of what we're going to touch on with why you keep shipping coal to a nuke plant, that's going to build off of, again, how do we replace other fossil fuel services? So in terms of where to start, I don't know, man. I really don't know, but I think the highest yield stuff would be, let's maybe start with this whole question of, again, replacing fossil fuel services. What's the missing link? Because the mainstream view is we need to electrify everything. So maybe we can start by just starting to potentially poke some holes in that. BF Randall was saying, listen, electrification, that's 15% of global prime energy. So we have this 85% black block of process heat and everything else that we use energy for. And I think at its core, that is what your mission is, if I'm not mistaken. So why don't we just jump in there, and then maybe we'll take some sidetracks talking about renewables, talking about Euro EI, et cetera.
I guess, when was it 2007? I watched An Inconvenient Truth and became concerned about climate change. And I was wondering why they didn't talk about nuclear. So as part of that, I was like, okay, so why not? So I started doing the math to try and figure out why we weren't using it. I knew that the fast reactors were pretty close in temperatures and pressures as most fossil plants, at least the older ones. The ones built up probably until about 85. After 85, the newer plants tend to be supercritical, so higher temperature, higher pressure. But they're, it's just changing out a turbine. It's not there's cost with that. I can't just be like flipping, just changing out turbines. So it's not direct drop in. But so it's like we have all this infrastructure. Nuclear energy is just a fancy way of boiling water. We've boiled water with oil. We boiled water with gas. We boil water with coal. We boil water with sunlight. All these things are all different ways that we boil water, and we use that. And wood. That's the other thing we use. We use wood. So all these things we use to boil water. So I was like, all right, so let's just swap out the heat source and try to preserve as much infrastructure as we have. Vaclav Smil talks about in his energy transitions the role of infrastructure, and that's something I don't think we really appreciate and that we really need to take a close, hard look at, because what we have been given in trust. We've been given in trust for the future generations, and we have been given tremendous assets that have taken. I mean, if you think about the Industrial Revolution was about 320 years ago is when the Industrial Revolution started, when Newcomen made his steam engine. So it was 1719, 300 years ago. So yeah, so just over 300 years ago since the beginning of the Industrial Revolution, if you put that at that time. So in that 300 years, all those generations have given us this tremendous infrastructure. And all of it centers around steam. Well, most of it. We've kind of diversified a little bit with the invention of the Brayton cycle, but really steam drives modernity, and it has. The bulk of electricity production is steam driven. So if we've got an issue with where we're getting power from that produce the steam, why don't we just swap out the heat source? So that's what kind of was my entree into, let's look at repowering all these coal plants. And so I looked at doing that. I didn't have a lot of ideas associated with it other than just kind of as a general concept. Really, what became my PhD was how you physically go about doing that. And so I had to create a technology that would enable that. And the purpose of that technology was to limit the regulatory purview of the NRC. I'm an American, so our nuclear regulator is the Nuclear Regulatory Commission, and so I wanted to restrict the scope of their regulatory purview to a very clearly defined island, and that anything that's outside that island is outside of their scope. They have no right to regulate it, and that actually proved to be. The solution that actually proved to be pretty elegant, and it also solved an energy storage problem.
Well, that's one of the big criticisms of nuclear, that I hear from some doubters is, it provides baseload power. That's great, but demand is elastic, and in some ways, I mean, I think there's some problems with these claims, but in some ways, nuclear is not dispatchable, just as wind and solar are not dispatchable. I mean, obviously, with nuclear, you're building peaks rather than filling troughs and building peaks, but that is an issue. So it sounds like you were involved or have been involved in thinking about that and trying to solve that issue of
yeah. Well, and nuclear is like BWRs, boiling water reactors. They actually load follow really well, because they are very stable in terms of power. So the mantra that we have is that reactor power follows steam demand. And so with boilers, I mean, it is very tightly coupled. There is no lag between reactivity insertion, reactor power change, and feed water flow rate change. So they're tight.
I guess the idea is that it's most economic to just use every single megawatt you can crank out of a nuclear plant. I mean, until and unless we have an excessive number of nuclear plants. I guess kind of how France does things with their, winter demand peak and then sort of having really shitty capacity factors and, not doing too much in the summer. But anyway, getting onto a bit of an aside, but I think that's a core contribution of yours with the, taking what we have from concentrated solar, CSP, and saying, well, fuck, why can't we use molten salts alongside nuclear as an energy storage medium? Is that correct?
Yeah. Genuinely, I have to give the people who are in the renewable and in the alternative energy business, some of them are actually really good engineers. And to give credit where credit is due, and legitimately credit is due, the development of concentrated solar power was phenomenal. Uh, and how I got turned on to it was I was just looking for energy storage, and then I found concentrated solar power. I'm like, wait a minute, this is the exact same temperature as this reactor. That literally one for one change out. And so then I just started playing around and tinkering with it, and then did a few tweaks for the nuclear stuff. But really, that was about the whole genesis of what it has become. Natrium was, wow, these guys actually did it. And then I looked at the materials that they had in there. It was nothing exotic. It was like stainless steel 316. Seriously, this is like everywhere. Or 307. I mean, it's like, it was beautiful. I mean, it was so straightforward. And
So why hasn't it worked out? Like, I mean, you hear about the CSP experiments in the US and they've been shut off really early because they weren't economic. Just briefly, why hasn't it
their
worked
heat
out
source
for
is
solar?
crap.
Okay.
Their heat source is the sun. You have to put it in dry, arid places. You're plowing up the desert. The desert in the southeast, if you've ever been out there, I do suggest you go. It's not desert. It is like this vibrant ecosystem. And you're plowing up hundreds of acres of this for all your solar panels. It's pretty ridiculous. But their heat source is absolute crap. Um,
And that's
I mean, it
mostly
only
because of
shines.
intermittency?
Well, I mean, yeah, it only shines what, half the day at most. Well, maybe in the summer a little bit more in the northern hemisphere, but other than that, it at most you're only the sun is only shining half the day, and of that, you only have enough high enough flux. You know, maybe 3/4 of the day you get a reasonable appreciable amount of solar flux. Other than that, of those three quarters of that 12 hours, that's it.
So this is what strikes me as interesting, and I want to talk to you about comparing thermal storage versus battery storage. You've mentioned that briefly in a tweet. What a great chance to expand on that on a podcast. But the whole issue with the impracticality of storage with a renewable system is that what's Europe going through right now? The Dunkelflaute or wind drought or the doldrums of winter. You're talking about week long, multi-week long seasonal storage. But with nuclear, because it's so reliable, we are only talking about hours of storage. It doesn't get into days of storage. And that becomes a much more solvable problem, it would seem.
Yes, it is, and it's even more than that. So in my dissertation, I talk about it as being an energy server. And so the analogy here is I don't know how familiar you are with computers. We have things called RAIDs. I don't ask me what that stands for. Something independent, array of independent devices. What the R stands for, I don't know, but the last three I got. Um, but it's basically when you have hard drives in parallel with each other, and they share the data in between each of the hard drives, so that if one hard drive fails, you just pull that hard drive out, and then your data is still protected, and then you can plug a new hard drive in, and they're hot swappable now. So they're highly reliable. So you use that for maintaining something that requires a high level of reliability. And so when I was looking at this, is that the salt tanks acts as like a bus, and on the bus you can have multiple things in parallel with each other. You can have multiple steam plants on the outside. So if you have a forced outage on one of your steam plants, it's not going to take down your total power output. And then on the heat supply side, you have multiple steam plants or multiple reactors supplying heat. And then those, if one of those goes down due to a forced outage, you still have the other 3 or 4 reactors there supplying the heat. So you've got this massively independent thing where they're all sharing this common bus with that storage to buffer in that time in there. And it turns out you don't need as much storage as you need with renewables, because your heat source is always there. I'd even looked at integrating combustion turbines with the energy storage system, where you take instead of having a heat recovery steam generator on a combustion turbine like you conventionally have, is you just have a salt heat exchanger. And so you fire up the combustion turbine, it's operating in a simple cycle mode, but you're recovering all the heat into the salt from that into the salt tanks. So now you have simple cycle flexibility on a combustion turbine with combined cycle efficiency when you integrate it with a storage system. and you have an extra way of dumping even a little bit more heat into your tanks. So that way you can play with more with the levels of where you have how many reactors you have, how big your thermal plant is, how big your storage is, and then you can scale it out. I mean, it's basically a mix and match. And so the whole idea was to increase the reliability so that if the plant goes down, that really would be an act of God. But if the plant does go on, you have so much stored energy on site, you can bring it back up. It's called black start capability.
Right.
So the whole purpose of this site was to be black start capable, so that you can restore the grid with it, but it's so reliable that the grid never goes down with it either. So it's like, oh, what is it that you want? Well, you want something that's never going to fail, and if it does fail, it'll bring itself back up.
So just, without getting into the nitty-gritty of reactor physics, I'm sure some guests would love that, but let's talk a little bit about why sodium fast reactor. It sounds like part of that is temperature. It's also super cool to extend the EROEIs and close the fuel cycle to the degree possible. My biases, as my listenership is probably very aware, have been on like let's keep going with the pressurized water fleet, at least to restart and reboot our industries before we get ambitious and work on technologies that may take a while to get high capacity factors, just because of taking a while to upskill our human factors. I mean, I had Noah Retberg on recently, and he was talking about precisely the contribution of the highly skilled folks that are nuclear submariners who kind of retire out and have a couple decades worth of work left in them and help run that fleet. And that's part of what has got America's PWR fleet to these 92, 93% capacity factor levels. So I've really neglected the advanced nuclear side of things. And so if you can be part of that education without going into deep reactor physics, but just talk about why you like sodium reactors, fast reactors, and why that couples in to replace coal, et cetera. I think you've hinted at some of that in terms of similar temperatures, et cetera. But go ahead and kind of sell me on that, or convince me.
Okay. So light water reactors, you're really kind of limited to about 260 degrees Celsius. And that's kind of like, you might get a little bit more, a little bit less, but you're in the neighborhood of that. Fast reactors, sodium fast reactors specifically, you're talking pool temperatures that are 500 degrees Celsius with steam temperatures of 450 degrees Celsius. So you're talking a lot hotter. Which allows you to be able to be more efficient with your turbine design, because you've got superheated steam, you've got reheat, you can play around with it. So that's one. But really what it comes down to, and this came out of Argonne National Lab with their integral fast reactor project, was this. The problem that had plagued sodium fast reactors in the past was that they were built like they were pressurized water reactors, where you have your reactor vessel, you have loops that go out to your intermediate heat exchangers that have another loop that go out to your steam generators, because sodium and steam react explosively together. That was another part of the reason why I got used to salt with this reactor, so that you can get away from that. So you have all this. Where was I going with this? So the old school designs, so like Fermi, if you look up Fermi, you'll see the day that we almost lost Detroit, as referenced in there. They had a partial meltdown, if my memory serves me.
This is not the Chicago pile, is it? We're talking.
This is the Fermi reactor that was up on Detroit. It was a sodium fast reactor.
Okay.
Then you have Clinch River breeder reactor.
Okay, did we almost lose Detroit, or was that
that was just what they said? I'm pretty sure that the reactor had a partial meltdown on there. So there's I'm showing my nuclear ignorance as much as I am a nuclear junkie. I am very ignorant on some things. So
fair.
And then Manju had an issue where they had a sodium fire from a leak in a temperature probe. So basically, if you have a system that's in a pipe, whatever's in the system is going to get out of it. It's Murphy's Law. It's just going to happen. And it does happen. So we'd have steam leaks. You'd have to deal with steam leaks on board a ship. You'd have water leaks, but I mean, you're going to always have that sort of problem. And so what they did at Idaho National Lab with Experimental Breeder Reactor 2 was they said, all right, let's get rid of these loops concept and let's just have a pool. And so they put it in this pool. So the reactor is kind of down at the bottom in the center part of the pool, and it's got a chimney that goes up so that heat rises. So it goes up the chimney. So the sodium flows in through the bottom, gets heated by the reactor, and it rises up because it's less dense. Yeah. And then it goes out, and then you have the intermediate heat exchangers actually physically in the pool that are high up, and then the sodium goes down through there, gets sucked in the pumps, and injected back in, and it just loops. So there's nothing outside of that, and that's in a hermetically sealed steel cylinder with no extra penetrations other than those at the top coming down and in. So your risk of a sodium leak is like zero. And not only that, is that you have two walls. So you've got an inner wall and you've got an outer wall. And so you've got a 2-layer protection to atmosphere from that if you even do get a leak from the inside of your containment. So it's in terms of that, I was like, okay, that's great. The other part of it is that water you have to get to really high pressures to get it to not boil. So in terms of pressurized water reactors, 2,500 psi. Please forgive me if I don't know that number in bar off the top of my head for all you SI junkies out there. But so 2,500 psi is pretty typical for what you'll find in a pressurized water reactor. Boiling water reactors are going to be around 1,000 psi, just because of where the steam turbines are designed for those systems. So, because that's the saturation, that's associated with the saturation temperature for the steam at that pressure. So the reactor's at saturation temperature for boilers. So you have your primary coolant in both of those reactors is pressurized. Anything that's pressurized is going to try even that much harder to get out of it. Well, with sodium systems, the system's not pressurized. It has a slight pressure on it, maybe about 3 psi, 4 psi. So what would that be, like so bar is about an atmosphere. So maybe a tenth of a bar or something like that. Just very minuscule pressure just on the top, just to keep air from coming in, and then just put an inert gas in on the top of it and leave it alone. And so it's very, very low pressure. While the sodium's hot, it has a relatively low enthalpy because it's not pressurized. And your boiling point for sodium is so much above where you would ever see that you're not going to be at risk of boiling the coolant. So you don't have to worry about it being as pressure tight.
So all of this points towards, I mean, obviously the PWR fleet is incredibly safe, but does it point towards savings in terms of, having to build lots of containment? Like what are the real
your
ramifications?
Your containment structure simplified because your piping is contained in this thing. The whole reactor module is shippable. So GE had 2 different module sizes. They had a 430 megawatt thermal and then an 840 megawatt thermal. The 430 megawatt thermal was rail shippable. The 840 megawatt thermal was barge shippable. And so the idea was to basically assemble this stuff in a factory, ship it to the site, drop it in. It's all seismically isolated and mounted. So in terms of seismic containment, is that it's completely, and you can't really do that with a pressurized water reactor because your systems are so spread out. But if your systems are so concentrated because they're in one little thing, you can isolate it that much better from the environment. And that's really where the benefits come from. So it's low energy, it's isolated. And then the other thing is sodium has a ridiculously high thermal conductivity, which means that it moves heat very easily. What they did at EBR2 was they started out with oxide fuel because that's
just for reference, in terms of the history of the development, we go EBR2 to IFR to Prism. Is that?
Well, EBR2 kind of became IFR.
Got you. Okay.
So, and really what IFR, and I'll get into that here in a second. So they started at EBR2 using oxide fuel, which is the conventional fuel that we use. It was uranium oxide, so it's UO2, and plutonium oxide as well. So it's a mixed oxide fuel technically. And they did that. They ran it, worked great. But oxide fuels store a lot of thermal energy in them because it's like a coffee cup, right? So your coffee cup is a ceramic. So this fuel is a ceramic, and ceramics are good insulators, which is why we use them for our coffee cups. But it means that once they get hot, they stay hot.
Yeah.
Because they have a lot of energy stored in them. And so what they did is in order to minimize that amount of energy that was stored in there, they shifted to metal fuel. So it was we use the word eutectic. Eutectic in metallurgy just means a mixture of different metals. And so you mix uranium with plutonium with zirconium, and you use those three metals together, and so it's an alloy. So it's an alloy fuel, and you cast it, and you put it in stainless steel tubes. And because it's a metal and you put a little bit of sodium in there to thermally bond it. So you have metal going to metal, going to metal, going to metal to get it into the coolant. And then from the coolant going from metal and with my design into a salt. So it's your temperature differences across that whole thing are very low because your thermal conductivities are ridiculously high because you're all dealing with metals. So you don't have the stored energy in the system. So when you have something bad happen, you can. One of the accidents that I ran was where there was a salt rupture on the salt side, and the reactor did not scram, and it just kept going.
Okay.
And
so
it's
the
called
salt being the coolant. Okay.
Yeah, being the ultimate heat sink. Well, effectively the ultimate heat sink for this. So the reactor did not scram. There was no protective action for it, and I ran it out for 7 days, and the reactor shut itself down. And so when you don't have that energy in the system, you can not do anything, and the reactor will shut itself down for days.
Okay, so I might be preempting this, but if SFRs, if sodium fast reactors, if this design is so cool, why hasn't it taken off? And I think it sounds like the only sort of economic deployed fast reactors. You mentioned Super Phoenix, and I think a Japanese experiment. The only ones that have kind of gone to market, it seems, are Rosatom's BN series, the BN 600, BN 800. First off, are those loop or pool? And how are they doing economically? And again, why isn't this concept taking off? Is it just because John Kerry killed it in 1994? What's your read on that?
The 800s are pool, and I'm pretty sure the 600s are pool too. The Russians are using oxide fuel in theirs, not metal fuel. Metal fuel is more of an American thing. The Japanese and the French also used oxide fuels as well. So really the innovation with the metallic fuel, I would attribute mainly to being an American one. There might be some other people who have done that, not to my knowledge, so please don't quote me. But so the reason why they shifted to the metallic fuel was because of the lower energy was one, but the other one was that it solved the problem with how you go about reprocessing the fuel. All these other ones, the reprocessing that they do is conventional uranium reduction oxidation, uranium reduction extraction.
Like what the French do at The Hague.
Purex and Urex. Say again?
What the French do at The Hague, is that correct?
Mm-hmm.
Yeah, okay.
Russia...
And you recover, 10-15% or something? Is that?
No, you get it all.
Okay.
You get it all. The problem that they have is that the minor actinides don't come. The plutonium comes over, but the other minor actinides don't. And then
just define minor actinides for those of us beginner minds.
Okay, so minor actinides. The other one that I'll also use to describe them are called transuranics.
Okay,
so
heavier than uranium.
So it's basically uranium. Everything past uranium. So neptunium, plutonium, americium, curium, berkelium. I mean, all the californium. So really, you kind of go up to about californium with reactors. So basically, neptunium to californium, that kind of that spectrum there. Those are your minor actinides. Well, yeah, the plutonium is kind of separate because it's special. But everything else is kind of considered your minor actinides. But I guess technically plutonium is also minor actinide or transuranic. So you'll see it MA as an abbreviation or TRU.
So I mean, are the Russian sodium fast reactors proving to be more economic or better than
I
the
don't know.
pressurized water fleet? Or I mean, certainly there's a bunch being built, but they're not the dominant Russian technology at this point. What's
Honestly,
your read though on the American front as to why we haven't? I mean, there's not been a new reactor licensed other than the AP1000 since the NRC was founded. Is that the issue? I mean, is it because the way you're painting this, it just sounds like, well, man, this is amazing. We can close the fuel cycle. We can use old waste or depleted uranium in these things. They're simpler to build, et cetera. I mean, nuclear, like unlike things like iPhones and information technology, power plants don't operate according to Moore's law. They obey more basic laws of physics and take much longer to, I think, for innovations to trickle down and to scale. Is that your read, or again, in terms of why sodium fast reactors aren't more ubiquitous or haven't made it further, maybe not just in the U.S. but in the West, like with the Super Phoenix, et cetera?
so in the US, what really held back sodium fast reactors was Hyman Rickover and his
Okay.
experience with Seawolf. That was a loop type sodium fast reactor.
In a
Naval,
submarine? In a
yeah,
submarine? Okay.
yeah, 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 yeah. The second nuclear powered submarine was a Seawolf, and that one was a sodium fast reactor. The Russians used a lot of metallic coolant reactors, like their Alpha class submarines were actually cooled by molten beryllium. So they were a thermal reactor that had a metal coolant of molten beryllium. I mean, the Russians really did some, at that time, Soviets did some really weird and wacky stuff. So in the U.S., I would probably put it at Hyman Rickover, and then experiences with Fermi, Clinch River breeder reactor also kind of hampered that. The French gave it a shot with Super Phoenix and Super Phoenix. I think they kind of lost the appetite for it because they already had 80% of their power coming from pressurized water reactors, and so they just kind of walked away from it. Manju in Japan had a lot of technical problems. And so the Japanese just kind of walked away from it. Again, it was the loop type reactors that really had the problems. Um, the Russians are building more of the BN 800s. So I would say that's a positive sign. I don't really know what the Chinese are doing. Um, but it, that so you talk about closing the fuel cycle. So the other, we didn't really talk about this, is what the IFR is. So you asked me about, was EBR2 was the predecessor for IFR? Well, EBR2 really was the IFR. It was the reactor part of the IFR and the fuel. And so they were testing the fuel, validating the fuel, doing all sorts of fun stuff with the fuel to qualify it. And that's really what they're using for Natrium, is the EBR2 experience. What IFR is incorporating pyrometallurgical processing, where you take a lithium chloride salt and you electrochemically dissolve the fuel once you chop it up in there. So the stainless steel won't dissolve, but the uranium, the plutonium, and all the other minor actinides will. And then you separate the uranium out from the others. It actually forms like this really cool, it looks like electricity or like lightning would look. It's called a dendrite. It's like this lattice structure of all these little tendrils that go out like hair. And then the minor actinides build up, and then you pull those out at a cadmium cathode, and they just dissolve in the cadmium, the molten cadmium. So you separate those two out, and then you're left with the fission products in the salt, and then you can just pull the fission products out of the salt. Fission products decay away in 300 years. There's no 10,000, 100,000 year that you have to hold it, because all those minor actinides that you pulled out of the cadmium cathode, you shove back into the fuel, and it's perfectly good reactor fuel. I like to think of fast neutrons as the honey badger of neutrons. They just don't care. They're going so fast that everything looks the same to them.
Another benefit of SFR, sodium fast reactors, there are concerns. I had Simon Michaud on. He's with the Finnish Geologic Survey. He's a bit bearish on nuclear because, he says, I mean, even if we could hit world record deployment and get 25 pressurized water reactors out the door every year, we're likely to consume at least our proven reserves of uranium. And there are certainly more to be found and lower ore grades, et cetera. But within 70 years, these anxieties about running out of uranium. I mean, there's also seawater extraction that's maybe possible, although, these are pretty dilute sources. But sodium fast reactors or fast reactors in general seem to be able to push out our, future use of uranium for a long ass time. Do you have a sense of how long ass that is?
To give you perspective, if the U.S. were to get all of its energy from uranium, so like let's just wave a magic wand. Magic wand, all U.S. energy comes from uranium. The U.S. has mined in its depleted uranium reserves from our weapons program and uranium enrichment for all the years that we've had nuclear power. We have enough energy without having to dig in the ground sitting as uranium hexafluoride to last us for over 2,000 years. Okay?
So let's confidently say it certainly extends our uranium reserves.
Yeah. So your waste liability goes to 300 years, and your fuel possibility becomes infinite. Where I see fuel cycles going is uranium is a really good fast fuel, and thorium is a good thermal fuel. So back in 80 something or another, Rickover pushed for what was called the light water breeder reactor. And he took a shipping port and put thorium oxide fuel pins in there and turned that reactor into a breeder. A pressurized water reactor became a breeder reactor. And so is that we're going to have to maximize what we call the conversion ratio. And conversion ratio is so what drives a nuclear reaction is called the fissile material, which means easily fissioned. So people will say fissile or fissile. It's the same thing. It's like potato. And so the fissile material is what drives a reactor for all reactors. Doesn't matter the type.
And that's uranium and plutonium, right?
Uranium-235.
Yes, and plutonium-239.
For naturally occurring uranium. Plutonium-239 for the plutonium. And then based off the thorium fuel cycles, uranium-233. So
Gotcha.
We have three predominant fissile isotopes. Uranium-233, uranium-235, plutonium-239. You could also throw plutonium-241 in there too, but you're getting the idea. So it's kind of like those odd numbered ones. Those are the ones that like to split apart. So the conversion ratio is how much of that do you have to burn in order to get more out of it? And so you want to have a conversion ratio above 1. So if you're above 1, you're a quote unquote breeder reactor. If you're less than 1, you're a burner reactor. So you have burners and breeders. All light water reactors now are all burners. CANDUs use natural uranium, but they're using the naturally occurring uranium-235 that's in as 0.71% of the uranium in there to drive those reactions. So that's CANDU. So I mean, I kind of lost track there for a second.
That's okay. You're talking about fissile, and you're probably going to get onto.
Okay, so fissile conversion ratio. So you get more. So CANDUs are burners. Pressurized water reactors are burners. Boilers, water reactors are burners. Fast breeder reactors are obviously breeders. So you have to get fissile material. So you can enrich uranium to get enough fissile material. So like 5%, 20% enriched. So you can enrich uranium to get it, or you can breed your fissile material if you've got a breeder. And so if you turn all your reactors into breeders, then you're producing all the fissile material that you ever are going to consume. And then with these reactors, you can play around with the conversion ratio based off of what the market conditions are. So if you don't have a market and you have a good inventory of fissile material eventually, then you can shift it to being more of a burner.
For the sake of the time we have today, I really want to get to something we were chatting about before, which is we've talked now about the role of sodium fast reactors, that we can simplify containment, shrink the emergency protection zone, I believe it's called. Planning zone. We can operate some higher temperatures, maybe get higher thermal efficiencies. We can dump heat into molten salts because we're getting a higher sort of steam output, et cetera, or just directly transfer into the salt. Okay. But you talk about, and you've talked about like the trillions of dollars of fossil fuel infrastructure that already exists. You were talking as well, I think obviously about the steam side of coal plants, but I think also about the potential for Synfuels and replacing other fossil fuel services. So here's where I'm curious, and you've planted this teaser, which is we swap out sodium fast reactor for the heat source for a coal plant, but we keep shipping coal there. Why? And is it just because you're a coal miner?
No, the reason why I'm a coal miner is because of what I figured out. So I got to here because I'm a nuclear junkie. It is this. Coal is an incredible source of fixed carbon. It is almost pure fixed carbon. Our coal and our mineral is about 65% carbon, and about 12% ash. So you've got sulfur, nitrogen, oxygen, carbon, all this stuff in there. So it's kind of a milieu of things. If you burn it, you have to deal with all the combustion products that come off of it. So nitrogen oxide, sulfur oxides, particulate because of the ash. I mean, and it produces heat. It works. It's what gave us our civilization. But I think coal is much more valuable as a liquid fuel. And the reason why is so when you gasify coal, you remove all the particulate, you remove all the sulfur, you remove all the nitrogen that's in there. You basically get carbon monoxide and hydrogen when you gasify it. And you convert that into liquid fuels. And if you use low temperature Fischer-Tropsch, what you end up getting is you get something that selectively creates jet fuel and diesel fuel. So kind of like those mid distillates get selectively created with low temperature Fischer-Tropsch. And so you then have this ability to be able to produce all this fuel. I went to a coal gen conference and presented an idea of, I live in Atlanta, and presented this idea of repowering the coal plant that was in Coweta County and using the nuclear reactors that I was working with and producing Synfuels there, and then installing a pipeline for the jet fuel to go up to the Atlanta Hartsfield Airport. So that one coal plant supplies more fuel than Atlanta Hartsfield consumes. So you'd be able to locally source your fuel.
And we learned from B.F. Randall, and I mean, I've subsequently heard this from several other prominent thinkers whose names I'm blanking on at the moment, but the relative value of diesel in particular as kind of the pumping heart of civilization in terms of all of the heavy duty vehicles that we run like around the clock, be it, hauler trucks for mining, trucks that deliver our food, tractors for agricultural, et cetera. These are really hard to replace prime movers, the diesel engine. So I get the rationale for selectively making this mid-grade distillate without having to make all this gasoline, which we're trying not to use because we're trying to find other ways to decarbonize transportation, maybe EVs, maybe something else. But what I'm not understanding here, and it's because I'm not a chemist and I'm a doctor and got the science education on the biology side, is this lower carbon, like as using this carbon source, how is this better? How much can you decarbonize with this approach, or do you even decarbonize with this approach? And then I'll have a follow-up question.
It depends on how you do it.
Okay.
So if you do it conventionally, it's actually more carbon intensive.
Interesting.
Even if you use nuclear heat for the air separation unit. So you have to supply heat into it. You save on energy using steam from a nuclear reactor. So you kind of play a shell game with where your heat sources come from. So you try to use the heat from the reactor as much as possible, but you're just slightly above break even on the carbon intensity using a nuclear reactor coupled with coal gasification in terms of the carbon intensity. Where you get your savings, and if you convert all the CO2 that you produce into carbon monoxide using electrolysis, and then source your hydrogen, the bulk of your hydrogen, also through electrolysis using, guess what? Nuclear reactor. So then what ends up happening is if you're doing that, you end up reducing the carbon intensity of the fuel by 28%. So all those hydrocarbon bonds that you're now making, because you're making all the an additional amount of carbon dioxide or carbon monoxide, and you're making all this hydrogen, that's a lot of hydrogen, you end up with about a 28% reduction in the carbon intensity of the fuel, because the carbon is just it's like a little battery. So each little hydrogen atom that you stick onto it acts as like a little stored nuclear heat. So you've got all these little batteries floating around in these hydrocarbon chains. And that's a heck of a lot easier to transport and deliver and do all this stuff with than with electric vehicle batteries. So you have a lower carbon intensity. So it's don't make the perfect the enemy of the good.
I want to see what you're comparing carbon intensity to, but what you're describing again to, I'm going to bring up some skepticism again without a serious engineering ability to assess the claims here, but it sounds, it's certainly not as Rube Goldberg-y as balancing a grid with intermittent energy, but it sounds like you have a bunch of processes running. They may have scalability problems. They may be not economic when they're all combined versus just drilling for crude per se. Although we are trying to maybe pay a bit extra to do a process that's less carbon intensive. Certainly, in introducing this episode, I was talking about pragmatic versus puritanical responses to decarbonization. And again, BF Randall really shone a light on this idea that, obviously there's a whole bunch of embedded emissions in a battery electric vehicle. The promise is over its lifetime, you might use a bit less carbon than burning gasoline for the life of the car. However, what he was pointing out is that, these are very mineral intensive processes, and there's a shit ton of diesel that goes into mining all of the elements that go into the BEVs. So I think what's important to emphasize here is that a battery electric vehicle is not a zero carbon device. There's a whole bunch of embedded carbon in it. It's not puritanical. It sure looks that way. It's marketed that way. It's flashy, but there is no sort of zero carbon vehicle out there. So are you comparing your carbon intensity with what you're describing to a battery electric vehicle or to a combustion vehicle? Or do we even know the true kind of embedded carbon in these different approaches?
I'm comparing it to oil.
Oil, okay.
So if you have to choose between liquid fuels, so if you're producing as much as theoretically possible, gasifying coal and using nuclear heat with the electrolysis that I was talking about. And electrolysis has some technical issues right now with scaling. So it works on small scales. I just did some back of the envelope calculations, and for like repowering a 1.3 gigawatt coal plant, if you were to liquefy all that coal into liquid fuels and have zero emissions coming out of the facility, you would need to have like about 1 million of these little electrolytic cells, and that's not practical. If you had 100, you could make it work. So there's an engineering scalability with the solid oxide electrolytic cells. So this is a high temperature, 700 degrees Celsius type reaction stuff. So what I'm saying, is it technically possible? Yes. Is it fully scalable at this point? No. However, you can start building the infrastructure out in order to get there, and then work on the technology and refining the engineering of that as you go along to try and increase your yields incrementally.
Certainly, it's more scalable than fusion. that's a bit of a joke here right now, but we had some news about
fusion.
Yeah, and it gets all the hype. I don't hear much hype about this. But another concern, and concerns about peak oil sort of got parked on the bookshelf as the fracking revolution took off. But fracking is the source rock. We're putting a really big straw into the end of the milkshake and slurping up a whole bunch. We're still facing peak oil concerns. So, if this is a replacement for crude, which, let's face it, is kind of the lifeblood of the world economy, maybe there's more of an impetus to do this. I guess I'm wondering about, is this viable? Bill Gates, in his book about climate, talked a lot about, paying the green premium, and that, if we just, he's very much kind of an investor class guy and a guy who believes in climate change solutions being sort of very market and consumer driven. But essentially, if we can, invest and innovate technologies, say between a gas vehicle and an EV, and get them to price parity, then consumers will make the choice, and it's going to just, will drive nicely downhill. Now, the green premium strikes me as thinking that's kind of of 2010 thinking, when all of our sources of primary energy dropped, peak to trough 90%, uranium, oil, coal, natural gas. We've been living a really cushy decade of low cost energy, low cost capital, very cheap credit. When we do these processes that are less economic, maybe a lower EROEI, if that is the case with what you're describing, are they actually viable in an economy that's kind of teetering a little bit, that's, hyped up on credit and potentially heading into, recession or kind of imposed degrowth? I know this is a big pregnant question, but interested in your thoughts.
So I'll try and stick to the more technical stuff. So has this been done at scale? What I'm talking about with the coal liquefaction? Yes, South Africa, Sasol. So South African State Oil Company, I think is what Sasol stands for. They are using basically Lurgy gasifiers with high temperature Fischer-Tropsch to produce predominantly gasoline, some diesel. So they have it optimized for what they need in their country. For Sasol, what they could do, if there's a South African out there listening to this, drop in some Natrium reactors in there and start shifting where you're getting your heat from in order to drive your chemical processes from a nuclear reactor. You have to get heat from someplace in order to do anything. So if you're taking some of your feedstock in order to supply your heat, then you're reducing the efficiency. But if you've got a heat source that's independent of your feedstock, then 100% of your feedstock goes into your product. And then you can start optimizing your process design for maximizing recovery. And really the fundamental feedstock with the coal is the carbon. So you can start then optimizing your process design for that. But the first step is change out your heat source. Another one would be in oil refiners. So oil refiners anywhere in the world, all their temperatures, for the most part, probably less than 600 degrees Celsius. They do have some stuff that's in the 700 to 800. But, Natrium gets you close. A little oxygen and some of your product will get you the rest of the way. So you're using a lot less of your product in order to drive your process. So again, oil refining, you can drop your carbon intensity, or you can look at it from the standpoint that I like looking at it from, is that you are maximizing your product yield on a scarce resource. And so nuclear in any of those applications is going to help them do that. And that's something that they should be doing now with the Natrium reactor, because it works.
I've been very influenced by Nate Hagen's work. We're going to have him on in January. A podcast is called The Great Simplification. That's his podcast. And again, he's very concerned about kind of the end of economic growth occurring. I mean, A, because exponential functions lead us to consuming the entire energy of the sun. I think in 1,400 years of 2.5% economic growth, but B, because energy is the fundamental currency, and we are running into depletion of our fossil fuel reserves and declining EROEIs. I think what holds back nuclear is when there's abundant sources of fossil energy. And when we see those constrained, such as the OPEC crisis or the current energy crisis, all of a sudden nuclear is back on the agenda. Now, it's still facing a massive uphill battle because of the burden of regulation, because of incompetent industrial policy, because of incompetent energy ministers, or ministers of the ecological transition, as they're called in Europe, in many countries. But I'm wondering, let's get to a theoretical place where we're starting to see economic growth really constrained by hard limits on fossil energy and fossil fuel depletion. Do you think that, with a regulatory environment and industrial policy environment that's optimized for, holy shit, guys, we need to make up for this fossil fuel energy so our economies don't collapse, that, things like the Natrium could be deployed at scale quickly enough to do some of these processes? Because again, what you're talking about is an energy source that can do electricity, that can do load following and hopefully peaking to some degree, that can replace, I guess, some process heat applications, although a lot of fossil fuel processes are requiring thousands of degrees of temperature, but also be a feedstock for Synfuels to use our existing infrastructure, be it, the railroads that carry the coal to these sites, all of our, hydrocarbon infrastructure in terms of, gas vehicles, diesel engines, which really do seem to be unreplaceable.
Oh, they are.
Yeah. So
So here's
so I guess the
so here's
fundamental question is, could we, removing all of the human constraints, regulatory and just the idiocy of poor industrial policy and political cycles that don't allow long-term thinking, let's say all of that we could control and align, could you deploy these things fast enough to start to make up for declining fossil fuel inputs so that we don't crash the global economy and head into some terminal degrowth and all of the nastiness of, scarce resource competition and what humans do to each other when they're fighting over scarcity?
so I think what we're starting to see is, you were right, the energy constraints kind of limit where we are, and we're getting conflict through those energy constraints, because we're having to compete over those scarce resources, because energy is wealth. We are So when we compete for energy, we are competing for wealth. When we restrict energy to the developing world, we're restricting their access to wealth and wealth creation. So a lot of policies, I do a lot of work in the developing world as well. A lot of the policies that we have are actually about preserving the existing economic order in the world, by preventing the economic growth in the developing world, which is Central America, Latin America, Africa, and Southeast Asia. And it's a shame. So, waving my magic wand, we get rid of those barriers and we start rapidly growing energy everywhere in the world. All right, so what does this look like?
But can
Ships.
can you do that? Yeah,
Dude,
with
easy.
nuclear.
Oh yeah, ships.
So. Okay.
All ships. These things are massive. Nuclear power.
You're talking about like the big super carrier, obviously not little fishing boats, but you're talking about the huge Q class or whatever they're called that get stuck in the Suez Canal kind of boats. Yeah.
So like a VLCC, for your larger ships. I had a Twitter thread looking at using a molten salt reactor based off of the air nuclear propulsion program with a LM 2500 derivation gas turbine, where you're just heating air with the salt from the reactor. So that was basically what they did for the ANP. They're like, this would work on a ship, so why don't we do that? And so I have a Twitter thread on that one. So if anybody's interested in that,
so obviously
shipping.
We're again playing in this imaginary kind of no regulatory constraint world. But also, I think the most fundamental human restraint is precisely what Rickover gave us, which was people like you who are highly trained in nuclear and could transition into the civilian fleet, and the human resource constraint. We don't have gazillions of people that can run nuclear reactors on VLCC ships, for instance. I mean, that's I think probably the most critical constraint on a nuclear renaissance, particularly doing it in time to deal with the end of our carbon pulse or fossil fuel depletion.
I have trained thousands. Literally thousands of high school, 19 and 20-year-olds, how to run nuclear reactors. I've trained thousands of them.
In the Navy.
Thousands.
In the Navy.
In the Navy.
Very cool.
It is not rocket science. It requires, seriously, it requires a little bit of, you can't be stupid, but you have procedures. So what we train them to do is to follow the procedures.
It's like a pilot, I guess.
It's like a pilot. I'm also a pilot, so that's another thing in the resume. It's just,
what don't you do?
You follow procedures, and so you train them to follow procedures. You try to teach them to understand what the procedures mean. Some of them, bless their hearts, they try, but they don't get it. But they know to follow the procedures, and then the ones that do, those are the ones that you try to promote. And so you'll get a sorting in there, but really it's the procedures. And that's easy. It's just another technical application. It's not difficult. It's actually a lot of fun. So that's to get the operators. I don't see that as a problem. In terms of the reactors, so you said a lot of the process heat. So I looked at U.S. process heat use as part of my dissertation to try and figure out, how much could this energy storage, I called it nuclear thermal energy storage, how much market potential could that have in the process heat world? Turns out it's about 60%. So 60% of process heat use in the US falls below 450 degrees Celsius. You get into the 80% range when you go up to about 700 degrees Celsius. And then you have the outliers that are calcining and steel refining. And those are in the 1200 degrees Celsius range.
In the time we have left, and it's just a few minutes, give us the kind of Abel, pragmatic decarbonization plan that seems to also be puritanical from the perspective of getting us as low as possible, but not delusional about the fact that there's not going to be some embedded carbon and some fossil fuel inputs and maybe coal as a carbon input for Synfuels. But I think you've touched on it, but I think this would be a great summary. You mentioned nuclear propulsion for large shipping, Synfuels, but just give us that rundown in the time we have left here. The Abel decarbonization plan.
First, repower every single coal facility out there with natrium-based reactors. That also counts for molten salt reactors as well. I don't have a thing against molten salt reactors. I pick what works.
But so far we have much more operational experience with SFRs than molten salt reactors, and
yes,
we have actual ones that work versus. Okay.
So repower every single coal facility out there with that. Keep all the coal coming to those coal facilities and start producing liquid fuels using coal from the nuclear heat. Worry about optimizing as you go along. Every single oil refiner that's out there in the world, add nuclear reactors in there, and you'll cover about 90% of your process heat demand on the site.
And that's happening with Dow Chemical and X Energy, apparently. That's on the horizon.
Yes, and they're using a high temperature gas reactor, if I'm not mistaken.
Yes, that's the plan.
I'm not a big fan of high temperature reactors. I just don't like high energy systems. I like low energy systems.
Okay, but carry on with the plan.
Carry on. All right. So they've got repower. Use your heat for those things to maximize product yield. So the hydrocarbons are scarce, they're valuable. Maximize their recovery. Stop burning them when you don't have to.
Vital feedstock for 6,000 things a minute, a barrel of oil. Feedstock for all kinds of important shit, like fertilizer, for instance. Although maybe we can decarbonize.
Well, you can decarbonize a lot. So you can actually shift Haber-Bosch to be entirely nuclear powered with electrolysis. So it's just sourcing the hydrogen. So cheap source of hydrogen, methane. Okay, let's use water. So you can use nuclear as much as possible in these process applications like Haber-Bosch. So now, as you're starting to optimize, so you've shifted effectively electricity away from you've decarbonized electricity.
Yeah.
Out the get-go.
Yeah, that seems like the easy thing.
That's the low-hanging fruit. Next is you decarbonize oil production. And that sounds weird to say that, but the production and the refining of the oil is decarbonized. So the refiners aren't emitting carbon dioxide as they're refining the oil, because right now they're burning stuff in order to refine the oil. So stop doing that.
Yeah.
Decarbonize oil production. Use coal, continue to use coal because it's a valuable feedstock to produce more liquid fuels. So as your oil resources die, your coal ramps up. And so that you're able to really optimize your for your carbons, for plastics. I mean, plastics are huge. Oil.
Well, I'm a doctor. I know how key plastics are.
So you do that. So you're using nuclear as much as possible in that. And I'd say you'd probably be able to get, in terms of primary energy, pretty easily 70% doing this with nuclear. Iron refining is using there's a process out there called Midrex, which is a gasification, and you could almost even make that entirely closed loop, where you recycle the carbon monoxide and the hydrogen in there. So you produce make carbon monoxide and hydrogen from electrolytic cells. They reduce the iron, so they absorb the oxygen from the iron ore, leave the raw iron behind. That comes out of the reactor. Run that through an electrolytic cell, put that back in, and you just have a closed loop iron. So all these things you can do.
So I guess question for you again, we're playing in a big land of hypotheticals, which would require a lot of alignment in terms of industrial policy, etc. We've said that we've got that. Do you, based on your knowledge, in the fossil fuel industry as well, just as you can't build a wind turbine with a wind turbine in terms of powering all the processes that go into the supply chain to build the wind turbine, certainly as you build out this nuclear dreamland, we're talking of, it's fossil fuels are going to supply most of the energy to do that, whether it's the metallurgy or, just every goddamn fossil fuel service there is, and there's a fuck ton of them. Do you think there's enough fossil fuels left to do that? Or are we going to consume all of those remaining hydrocarbons just to get the system booted up?
There's enough.
Okay.
There's enough fossil fuels to get us there. I do think.
Yeah. But we need to act with some urgency and align on this.
Yes.
Yes.
What we do have is valuable, and we need to be smart about how we use it to really do that energy transition. Do I think we have a little longer than what we might feel like? Probably, because we haven't really kind of, like with coal, we have the easy stuff that we've mined has been easy. We haven't mined the hard stuff, and the hard stuff's still there. And then there's hydrocarbons everywhere, so we'll find them. We'll figure out ways of extracting them. I'm not as worried about that, so I think we've got some more time. But prudence is, if you've got something that's valuable, don't waste it. And the hydrocarbons that we have are valuable, so don't waste them. Burn them where you want to burn them. Burn them in your mining equipment. We are not ever going to stop mining. Yes. We are going to be mining until we are no longer a species.
Yes, sir.
We're going to be mining asteroids here pretty soon, God willing. But I mean,
maybe seafloor first, but anyway, yes.
Yeah, mining, dude. That's
diesel powered. That's diesel.
And
I mean, this was funny because, after that Randall episode, we had people saying, okay, yes, diesels provide high torque at low RPMs, but hey, electric motors can do that too. And then I learned about these hauler trucks, and they are fucking electric generators that power electric motors that turn the wheels, just like a diesel electric locomotive.
Yep.
So no, it's not, not that. And obviously the haulers, we also had Geoff Russell write a nice article inspired by our BF Randall's episode, which was looking at the charging times for these vehicles. If you were to run a battery hauler with a 19-ton lithium-ion battery, they only run for about 55 minutes before needing a new charge, which makes mining completely uneconomical. I mean,
when you're running a mining operation and you're doing 2 shifts, you've got 2 12-hour shifts. Your mining equipment is running 10 hours on each 12-hour shift. So 20 out of 24 hours a day, your mining equipment's running, and you fuel them up at each shift turnover. Like they'll have a fuel truck and they'll just go to the next one. I mean, line them up on the big operations. You can't replace diesel for that. Airplanes, Jet A, incredible fuel, absolutely incredible fuel. You like flying? Commercial flights, all Jet A. And until we get like these hypersonic airplanes that are using hydrogen, we're going to be using Jet A, man. So the big stuff is Jet A for the airplanes and the diesel for the mining equipment. And so gearing ourselves to try and shift our focus towards preserving the things that can produce that will kind of maximize that.
I guess I'm what am I, a defensive pessimist? I've been diagnosed with that by Doomberg before. Anyway, I mean, scalability is a big question. I think we're running out of time today, Cal, but we've planted a lot of seeds, which we could, start tending, watering, growing, and chatting about a lot more. I'm just fascinated about nuclear submarines and running reactors on these vessels. And I've talked a little bit about that with Rod. But I mean, I can have you back just for an episode on that, but I look forward to all of the conversations that this episode is going to spark. I think it's going to be similar to the BF Randall episode. And I really appreciate your time. You're a busy guy. Pilot, what is it again? Strongman, competitor, coal miner, reactor designer. We're probably missing a few other things, but you got a lot of shit on your plate. So thanks for also now being a Decouple veteran, a Decouple podcast guest veteran. You can add that on the resume for whatever it's worth. Really appreciate you taking the time and having you on.
Oh, economist.
Okay.
We can talk. Yeah. I got pissed off at economists because they have no clue.
They don't appreciate energy. Okay.
No.
All right. We'll leave it on that.
Fucking clueless.
Note. We'll leave it on that.
So if there's an economist that listens to this, I am calling you out.
There's many, but we've got we've got some good nuke pilled ones. So anyway, Cal, we're gonna cut it for now. Thanks again for coming on.
Thank you.